In solid-state physics, understanding the vibrational properties of crystals is essential for explaining a wide range of material behaviors. Phonon dispersion relations provide a quantitative description of how these lattice vibrations propagate through a crystal lattice. These dispersion relations provide fundamental information about the thermal, mechanical, and electronic properties of materials. As such, it is important to understand a phonon spectrum or a phonon dispersion curve, which could be derived using these dispersion relations. A phonon spectrum, also known as a phonon dispersion curve, shows how the frequency of various lattice vibrations in a crystal, also known as the phonon modes, depends on its wave vector. Normally, the phonon dispersion curve of a material is very complex, and that is why it is customary to introduce this topic by using a very simple system. If you remember, in our earlier lectures, we have derived the phonon dispersion relation for a very simple system, that is a linear monoatomic chain of atoms, and that too restricted to longitudinal vibrations. This is the phonon dispersion curve of a monoatomic linear chain of atoms restricted to longitudinal vibrations. Then we gradually made the system a bit complex and we replaced a monoatomic chain with a diatomic chain, as a result of which the dispersion curve looks like this. Now, even for longitudinal vibrations, this dispersion curve has two branches. One is called optical branch, the other one is called acoustical branch. Phonon dispersion curve of real materials could be very complex. This is the phonon dispersion curve of gallium arsenide. You can see how complex it is as compared to a monoatomic chain or a diatomic chain. So these curves show how the lattice vibrations propagate through a crystal lattice, and that representation of the lattice in this case is in K space or reciprocal space. Normally these dispersion relations are plotted along a specific direction within a Brillouin zone. A Brillouin zone is nothing but the representation of a crystal in reciprocal space or K space. In this case, the specific direction is represented in terms of these letters gamma X, gamma L, gamma W, L, and so on. A crystal with large number of atoms in its primitive unit cell will have a complex Brillouin zone and large number of phonon modes. So it is not that all the lattice vibrations or phonon modes can be integrated in one such dispersion curve. There could be many such possible dispersion curves within a Brillouin zone, but due to the experimental limitations and theoretical complexity, it is practically impossible to capture the dispersion of all such phonon vectors, wave vectors, within a Brillouin zone. There are many experimental techniques such as inelastic neutron scattering, inelastic X-ray scattering that are used to examine phonon dispersion. But these techniques also cannot capture the entire 3D Brillouin zone. These techniques are often limited to certain specific directions within the zone and can only be used with specific sample types like single crystals. Even with theoretical calculations such as density functional theory DFT, the data volume required to represent the entire 3D Brillouin zone is very large, which makes the direct visualization of various phonon dispersions impractical. And that is why instead of trying to visualize the entire 3D space, theoretical studies are focused on plotting phonon dispersion curves along high symmetry directions within the Brillouin zone, as these are particularly important for understanding the material properties and are easier to analyze. Now let us understand what do we mean by high symmetry directions. Now these high symmetry directions are termed as K-path. K-path is basically a line joining various high symmetry K points in the Brillouin zone. Now what are K points? K points are specific points in a material's reciprocal space or Brillouin zone that represent different momentum states of electrons and phonons. There are discrete and finite number of K points in a material's Brillouin zone. Let us take an example. The first Brillouin zone of a simple cubic lattice is also a cube in K space and looks like this. Now, out of the various K points, some of the high symmetry points are shown here, like the gamma point, R point, and so on. So among the various K points in this Brillouin zone, the one is gamma point. This is the point of highest symmetry in a Brillouin zone. It lies at the center and denotes the origin of the Brillouin zone. Then X, which lie at the center of a square face at the boundaries. Then M, which lie at the center of a cube edge. R, which lie at the vertex of the cube. and so on. The most common and suitable K path is from the center of the Brillouin zone, that is from gamma point, to the center of the phase, that is point X, and then from the center of the phase to an edge, that is from X to M, then from the edge of the Brillouin zone back to the center of the Brillouin zone, that is from M to gamma, and then from the center to the corner of the Brillouin zone, that is from gamma to R. So the most common path is from gamma to X, then from X to M, from M to gamma, and from gamma to R. This path provides a good representation of the phonon dispersion relation, showing how phonon frequencies change along the directions of high symmetry within the crystal. Now if you move on to a FCC crystal, the Brillouin zone is a bit complex as compared to a simple cubic. The first Brillouin zone of an FCC lattice has a shape of a truncated octahedron, and some of its high symmetry K points are the gamma point, which lie at the center of this Brillouin zone, then X, which lie at the center of the square face, then L, which lie at the center of a hexagonal face of the Brillouin zone, then W, which lie at the corner point of the Brillouin zone, and then the K path would be from gamma, that is the center of the Brillouin zone, to L, that is the center of a hexagonal face, from gamma to L, and then from the center of the hexagonal face to a center of the square face, that is from L to X, and then from the center of the square face back to the center of the Brillouin zone, that is from X to gamma, and then from the center to one corner point, that is W. So the most suitable K path, or the most common K path in this case, is from gamma to L, then to X, then again to gamma, and then to W. So it is not that these are the only paths for the representation of phonon dispersion curves. There could be many such possibilities about which phonon dispersions or the dispersion relations can be plotted. Let us now have some general informations on phonon spectra, also known as phonon band structure, which could be useful from competitive exams point of view. Now if you want to know the number of branches in a phonon band structure of a certain type of lattice, how can we determine it? So there is a relation by which we can determine the number of branches in a phonon band structure. That will be equal to the number of atoms per primitive unit cell times the degree of freedom of the atoms in the unit cell. And if the number of unit cells used in the calculation is greater than 1, for example, we use a supercell having more than one number of primitive unit cells, then the number of branches in the phonon band structure would be n times the number of branches in the phonon band structure of one primitive unit. Among all the branches, there are always 3 acoustic branches, while the rest are optical branches. So, if we want to know what would be the total number of phonon branches in a linear monoatomic chain, we could find it using the above relation. So, the above relation says the number of atoms in a monoatomic lattice per unit cell would be 1, and that atom will have 3 degrees of freedom. So, altogether it will have 3 phonon branches. All 3 will be acoustical branches. There will be 0 optical modes. Among the acoustical modes, 1 will be longitudinal acoustic mode and 2 transverse acoustical modes. Now if you want to know the number of phonon branches in a linear diatomic lattice, then a diatomic lattice or a diatomic unit cell will have 2 atoms per primitive unit cell. Each atom will have 3 degrees of freedom. So altogether the number of phonon branches will be 6, among which 3 acoustical modes are there. 1 will be longitudinal acoustic and 2 would be transverse acoustic, and the remaining 6 minus 3, that is 3 optical modes will be there. There will be 1 longitudinal optical mode and 2 transverse optical. Now if we extend our lattice from a diatomic lattice to a triatomic lattice, a linear triatomic lattice, then how many phonon branches we could have in a phonon band structure of such a lattice? A triatomic lattice will have 3 atoms per unit cell. Each atom will have 3 degrees of freedom. So we will be having 9 such phonon branches, out of which we have 3 acoustical modes, 1 longitudinal acoustical mode and 2 transverse acoustical mode, and 9 minus 3, that is 6 optical modes, out of which 2 longitudinal optical mode and 4 transverse optical. Now if you want to know the number of phonon branches in a phonon band structure of a planar of a two-dimensional lattice, for example graphene, how can we determine that? The number of atoms in the primitive unit cell of graphene is 2. The degree of freedom of atoms in its primitive unit cell is 3. So the number of phonon branches would be 2 cross 3, that is 6, out of which acoustic branches will be 3 and the optical branches will be 6 minus 3, that is 3. And if we see the phonon band structure, it looks like this. These are the K points about which the phonon spectra is plotted. This gamma, M, K, gamma, this is the path, K path, about which the phonon spectra is plotted. These K paths are chosen based on the symmetry of the lattice. There could be other possible K paths also about which these phonon spectra can be plotted. So here you could see that we have a longitudinal acoustic branch, a transverse acoustic branch, and an out of plane acoustic branch or flexural acoustic branch. Similarly, we could have a longitudinal optical branch, transverse optical branch, and an out of plane optical branch. If we consider another two-dimensional material, for example, molybdenum disulfide or MOS2. The number of atoms in its unit cell would be 3. The degree of freedom of atoms in its primitive unit cell is 3. So the number of phonon branches will be 3 cross 3, that is 9. Number of acoustic branches will be 3. Number of optical branches will be 9 minus 3, that is 6. And the phonon spectra or the phonon band structure of MOS2 seems to be like this along the K path, gamma, K, M, gamma. You can see it has 3 acoustical modes: longitudinal acoustic, transverse acoustic, and flexural acoustic. Similarly, 6 branches, 2 out of plane optical modes, 2 transverse optical modes, and 2 longitudinal optical. Now, if you consider a 3-dimensional lattice, for example, gallium arsenide, the number of atoms in its primitive unit cell is 2. The degree of freedom of the atoms in its primitive unit cell is 3. So, the number of phonon branches will be 2 cross 3, that is 6. Number of acoustical branches would be 3. Number of optical branches will be 6 minus 3, that is equal to 3. And we could see that the plot seems to be like this. So, you could see that we have a longitudinal acoustic mode, a transverse acoustic mode, another transverse acoustic mode. So one longitudinal acoustic and 2 transverse acoustic. We have 2 transverse optical modes and 1 longitudinal optical. If you consider another 3-dimensional lattice, that is strontium difluoride, the number of atoms in its primitive unit cell is 3. The degree of freedom of atoms in its primitive unit cell is also 3. The number of phonon branches will be 3 cross 3, that is 9. Number of acoustic branches will be 3 and number of optical branches will be 9 minus 3, that is 6. And the phonon band structure or phonon spectra of such a crystal or such a lattice looks like this about this K path. These are the acoustical branches and these are the optical branches. Thus, we have seen the number of phonon branches reflects the number of atoms in the primitive unit cell of a crystal. We know that the number of acoustic modes is always 3, whereas the number of optical modes is 3n minus 3, where n is the number of atoms per primitive cell. So, by looking into the phonon dispersion curve of an unknown material or an unknown crystal, you can predict the number of atoms per primitive cell. Other than this, from the degeneracies and splitting of the phonon branches, you can reveal important information about the symmetry of the crystal in the reciprocal space. Let us explain it with the help of an example. So this is the dispersion, the phonon dispersion curve of aluminium. So aluminium is a monovalent metal. So it will have only 3 acoustic modes and will have 0 optical modes. Now degeneracy of phonon branches occurs when 2 or more phonon modes have the same frequency at a given point in the Brillouin zone. Now if you see here at the gamma point, all the acoustic modes lie at the same point. Now as you move from gamma to X, now X, if you look into the Brillouin zone, the first Brillouin zone of aluminium is an FCC crystal. So it will have the first Brillouin zone of aluminium is truncated octahedron. X is a point at the center of the square face having the coordinates pi by a 0 0. So while moving from gamma to X, gamma has the coordinates 0 0 and 0. So this direction, this corresponds to the crystallographic direction 1 0 0. Now you see, as you move along 1 0 0 direction, the transverse acoustic modes overlap each other. So we can say these 2 transverse acoustic modes are degenerate along 1 0 0 direction. Similarly, at this gamma point, while moving along L, where L is the center of the hexagonal face having the coordinates pi by A, pi by A, pi by A in reciprocal space. So if I move from gamma to L, means we are moving along 1, 1, 1 direction. So here also the two acoustic modes are degenerate. That means the 1, 0, 0 direction and 1, 1, 1 direction are high symmetry directions. Whereas you can see if you move from gamma to K, K is a point at the center of the edge joining the two hexagonal faces. It has a coordinate 3 pi by 2, 3 pi by 2 and 0. So while moving from gamma to K, we are basically moving along 1, 0, 1, 1, 0 direction. So here along 1, 1, 0 direction, the TA modes or the transverse acoustic modes split. They are no more overlapping each other. They split it. They get splitted. They are no more degenerate. That means the symmetry along this direction is relatively less as compared to 1, 1, 1 and 1, 0, 0 direction. Other information is from the slope of the acoustic branches. We know that from the slope of the acoustic branches near the gamma point, that is in this region. In this region, the acoustic branches are linear. So the slope of the acoustic branches near the gamma point gives the speed of sound in different crystallographic directions. So if you are moving along the path gamma to X, that means it is along the crystallographic direction 1, 0, 0. While moving from gamma to L, it is 1, 1, 1. While moving from gamma to K, it is 1, 1, 0. From the slope of the curve near gamma point along these directions, you can predict the speed of sound in along these different crystallographic directions. The slope of the linear region, which is nothing but d omega by dk, is basically the group velocity. So this is the group velocity of the acoustic wave, which is the speed at which the sound propagates. Now, since the slope of this curve, of the phonon dispersion curve, varies with direction of the wave vector, the speed of sound can be different along different crystallographic directions. There is one more valuable information that can be extracted is this gamma point is a very special point in the crystallograph, in the crystal lattice, that is at k equal to 0, where the phonon frequency is always 0 for acoustic branches. Now, if you are trying to plot or if you are investigating the phonon dispersion curve of a new material or a novel combination, and you found that at gamma point the phonon frequency is negative or imaginary, then you can predict that the structure is dynamically unstable at 0 Kelvin. This is a very valuable information that can be extracted by studying or by investigating the phonon dispersion. Like this, there are many such inferences that can be drawn using phonon dispersion curve. It reveals the structural details, lattice stability, elasticity, thermal transport properties, electron-phonon interactions, and even phase transition behavior. So, phonon spectra is very important, or investigation or study of phonon spectra is very important in understanding the behavior of crystals. And that is why a phonon spectra acts as a fingerprint of a crystal. We will stop here. I hope I could able to deliver some valuable information about phonon dispersion curve, so that next time whenever you see such a curve or any phonon dispersion curve, you could able to draw some inferences. I will discuss some different topic in another video. Till then, thank you very much. If you like this video, press the like button, subscribe this channel and press the bell icon so that you don't miss any notification. Thank you.